All right, so where have we gotten to in terms of background removal? Well, it would seem that this magical RBKG parameter needs to be big enough to do a good job. That is, if we choose a number that's too small, that leaves behind a whole bunch of stuff down here in the region where where it's not data, right? There aren't atoms down here. So, so it would seem that then the naive answer at this point would be make RBKG as big as possible. Well, that's probably not the right answer either, but let's give it a shot. Let's choose what I know to be an absurdly large value for RBKG of 2. And I'm going to plot the two things together just like I did before. And we see now that by choosing a value of 2 for RBKG, we have made a dramatic change to the data in this somewhat low R region. That is, we've completely chiseled out this peak and removed it from the data and had some impact at higher frequencies also. So it would seem that there's a problem with making RBKG too big in that you run the risk of damaging the data. XF span. I like that. You run a risk of, I didn't know there were fans. That's the thing. You run a risk of damaging the data. That is, to the extent that you believe that this peak is part of your data, the choice for the red line is obviously problematic because you've cut all of that data out of, all those Fourier components out of the data. So again, it's useful to go back and look at the data in energy. And we see that in the case of the RBKG of 2, that the red line now is starting to look like the data. You see how it really is doing a fairly good job of following the oscillations in the data. So now we've given the red line, we've given the spline enough freedom to start to approximate the data. That is, the spline now has Fourier components in it that we associate with the data. So the more complete answer to how you choose the value of RBKG is big enough to do a good job of removing the low frequency stuff, but not so big that you damage the data. That's another one of these sort of vague, not exactly clear criteria for how to choose things. And so what's the real answer? Well, I'm afraid that at the level of Athena, where we're just processing mu of E data, and in fact, nothing explicit about the data processing that we're doing right now has explicit knowledge about what the surrounding atoms are. That is, we're only dealing with the data and we're not thinking about modeling the structure. We don't have any more information than what I've shown you so far. The only information we have is this is the data, and when we click the R button, this is the Fourier transform of the data. So really at the level of processing the data in Athena, the best I can say, in fact, is big enough to do a good job, not so big to damage the data. Now, there are some ways of testing that. And as we can make that a little bit more numerical than what we've done so far. So 0.2 was obviously wrong here. So we'll try 0.4 and plot them together. And it looks like that, and there's still a lot of stuff left down here. Although, again, I want to draw your attention to the fact that using the too small of a value of RBKG has a big impact here, some impact here, but once we get to about here, none of the rest of the Fourier components change. So picking the wrong value of RBKG has an impact on the low frequencies, but not such an impact on the high frequencies. That's an interesting point. But I would say that 0.4 is still not the right value. But what I'm driving at is that you can increment this up. and just see what happens as you change the value. And here we got up to 1.6, and we see that things are starting to look really quite similar now. And if I'm going to just jump to the other side and do 1.2, and we'll look at that. Again, really quite similar. There are some details here that are different, but basically the Fourier components in this first peak remain unchanged from 1 to 1.2. I'll step up a little bit more and plot it again. And now at 1.4, bad things start to happen. So is 1.0 better or worse than 1.2? I'm not really certain right now. 1.4 is certainly wrong. 1.0 is probably a fairly safe value. You're doing a good job. 0.8, 1.0, 1.2 did basically the same thing down here. The details were slightly different, but it did basically the same thing. So what's the real answer? What's the real answer for how you know if you've done the background removal correctly? Well, the real answer is that we don't have enough information yet. And the reason that I say that, the reason that I say that is because we haven't done actually any data analysis. So I want to rephrase the question. The question isn't, what's the right background removal? The question is, how correlated is the background removal with the parameters that you ultimately want to extract from the data in the first coordination shell? That is, ultimately, you may want to analyze these data to get coordination number, bond length, sigma squared, the parameters of the fit, the structural information that you want to get from your data. There are some set of parameters that you're going to use to describe this first peak in the data, the things that we're going to learn about tomorrow when we start looking at Artemis. And clearly, if you were to analyze the blue and the red, you would come up with different values for coordination number, obviously, because the red one is so much smaller than the blue one. Probably you would come up with different values for sigma squared, and possibly even different values for delta R, for the distance between the iron and the oxygen atom. So clearly, if we go all the way out to 0.4, the background removal is correlated with the parameters that we want to extract from the data, because n changes dramatically between the blue and the red. But if we choose a more modest value of RBKG, something in the 0.8 to 1.2 range, where the Fourier components in this region weren't really changing very much, it was just the details down here, I think you'll find that as you change RBKG from 0.8 to 1.2, whatever values it is that you will extract from the data by analyzing this first peak won't much change. And that is the definition. Ultimately, that's the definition of a good background removal. Something that does a reasonable job of processing the data, but isn't too highly correlated with the numbers that you actually want to measure from your x-axis data. So the criterion about removing the background ultimately isn't about making the low R peaks look pretty, right? It's about not changing the answer when you ultimately do the data analysis, not changing the answers that you get by virtue of what number you choose right there. If I choose 1.4, I will change the answer. And if I go back to 1.0, then I will change the answer again. I'll change it back. But if I change over that range of values where not much was changing in here, then the details of the background removal will not be highly correlated with the details of the data analysis of this peak. And that is the definition of a good background removal, right? And the difference there is the difference between aesthetics and statistics, right? Making the low R region look a certain way is an aesthetic argument. And I often joke at this point that if the aesthetic argument were the one that you wanted to drive your data analysis, well, you'd be better off using Photoshop than Athena. But that's not the criterion. The criterion is a statistical criterion, right? Science is about statistics. And the statistical criterion of not changing the answer in the analysis of this peak by virtue of how that number is chosen, that's really the answer. But at the level of Athena, you pick a number that's big enough to do a good job and not so big that you damage the data, and that's the best you can say at the level of Athena. There are a few other parameters that affect the details of the background removal. One of them is the spline range, so the range over which the spline is evaluated. In the case where you have, well, what I had drawn on the board with the L3 and L2 edges, if you have that scenario where the data goes up at the L3 edge and then up again at the L2 edge, you would want to take some care to choose this number such that the spline wasn't required to follow the data up the L2 edge. So that's a situation where the default value is something that would have to be modified. But it would be really obvious because you would plot back in energy, you would plot here, and the background function would look ridiculously wrong because it was trying to go up the edge. You would notice that immediately. And the solution is to change either that number or that number. These two lines are not independent. Right? 14.8 is 842 volts above the edge, and when you change the one number, the other will change. I'll demonstrate that actually if I see how, as I change the value in K, the value in E changed along with it. Because there's a Fourier transform involved, right? The spline is determined by doing a Fourier transform and minimizing the low frequency components. Because there's a Fourier transform involved, there is a Kweight that we can apply to the Fourier transform. Now, for the newcomers among us, perhaps I should step back and explain what is meant by Kweighting. So I'm going to go back to the, not the copy, but the good one. So up here, close to the edge, the wiggles are really, really big. Right? It's really easy to see that there are oscillations in the data. Out here on this scale, well, okay, here you can still sort of see that there are oscillations. Out here, they're starting to get to be really small. But the amazing thing about all of this is that our beamlines these days are good enough and stable enough and with enough flux that there's actually signal out here in the flat part that's reproducible. And when I go and plot that data in K, you see that I've got wiggles all the way out here. This is, right here is about 400 volts above the edge. That is, it's about 400 volts above the edge then is about right here, about the region where it's getting hard to see that there are wiggles. But when I plot them in K, you see that there are still really clear oscillations well beyond 10 inverse angstroms, or about 400 volts. There's still these big wiggles out here. And these are reproducible, as we'll see in a second when I import some more of this lepidocrosite data. However, what I'm plotting here is not actually chi of K. What I'm plotting is the K-weighted chi of K. K-squared weighted, in fact. And what that means is that at 10, I'm multiplying by, well, at 5, I'm multiplying by 25. At 10, I'm multiplying by 100. And at 15, I'm multiplying by 225. That's right, isn't it? I think that, thank you, Fred. So that serves to enhance the signal out here where it's become really small, but still reproducible compared to the size of the edge step. So here's what chi of K actually looks like. Chi of K actually looks like this, where the wiggles are big, where they were big in mu of E, but they get really small and hard to distinguish from a flat line. But as we progressively amplify the wiggles at high K by multiplying by K weighting, K single K weighting, and K squared weighting, we are in some sense amplifying the size of the wiggles out here relative to the size of the wiggles up here. That is, there's a really good reason to do that in terms of the data analysis, but I'm a long way away from being able to motivate the really good data analysis reason for doing it. For the data visualization reason is that by K-weighting, we can actually see and examine and evaluate the statistical quality of these oscillations up here when we do k-weighting. And without k-weighting, it's hard for the eye to actually see that there are wiggles up here when plotted on this scale. So k-weighting is certainly a visualization tool, but there's a darn good reason for wanting to do it also. So the Fourier transform changes somewhat as you change the k-weighting because, well, you change the shape of the function that you're Fourier transforming. So here's the Fourier transform with k-weight of 1. Here's the Fourier transform with k-weight of 2. It's basically the same thing. It's just, you know, the relative shapes of the different peaks are slightly different. A useful new feature of the software is in the plot menu, current group, there's a thing that says R123 plot. And this just plots the Fourier transforms with all three k-weights. So this is k-weight of 1. It's not labeled in a very sensible way. K-weight of 1, k-weight of 2, k-weight of 3, with 1 and 3 scaled to plot on the same size plot as k-weight of 2. The reason I'm showing you this is to show you that as you change the k-weight, you do somewhat change the relative sizes of the peaks, and just sort of all the details change a little bit from the different k-weights when you do the Fourier transform. So that's why I showed you this plot. Why am I talking about this point? Well, the reason I'm talking about this point is because one of the parameters that you have for background removal is a k-weight parameter. And these k-weights over here are the k-weights that are used when you plot the data. This k-weight here is the k-weight that is used when the background removal is evaluated, right? The criterion for determining the background function is to do a Fourier transform and minimize the low R components. The value of k-weighting that is used to do that is this number right here. You will find that for these data that are really, really good data, this number just doesn't matter. You'll do a fine job, in fact, basically the equivalent job, with this value as 1, 2, or 3. But you will find in real data that has real noise and real problems with it, that it is sometimes useful to do k-weighting of 3, and sometimes it works out better with k-weighting of 1. And truth to tell, it's always a little bit mysterious which data prefer 3 and which data prefer 1. But it's another one of the things that you can play with to make the background removal work out well. That sounds a little bit scary. It sounds like I just told you that there are like knobs and fudge factors that you can change to make the background happen the way you want it to happen. And that's not what I mean. And I think I explained that a second ago when I explained what the criterion for a background removal is, which is that it doesn't damage the data, that the background is not highly correlated with the parameters that you get from the fit. And that assertion still applies. Yes, you can change this number and a few other things also, but at the end of the day, a good background is one that is not highly correlated with the parameters of the fit to the first shell. That criterion always holds. If changing this number helps you process your data, then by all means do so. But I have a hard time telling you a priori to give you advice for different kinds of data when you'd want to change that number. It's just one of the things that you can try. So you know, perhaps at some point this week you can import some of your own data and play around with it. With these data, you'll find that it doesn't make a difference. All right, that is, that's pretty much the whole story. Oh, E0. Yes, E0. Okay. Before I explain how E0 gets chosen by the software, are there any lingering questions about background removal? Yes?
Where does the background come from? I mean, what are you actually doing?
Oh, right. So, so if you have an atom in space, a single atom all by itself, no friends nearby, one lonely atom, there's going to be an edge step because you have a bound electron. And if the photon comes in and interacts with the atom, that deep core electron is going to be promoted into some continuum state. Right? So there is going to be an edge step. And that edge step is going to have some exponential decay because the more energy the incident photon has, the more likely it is that it'll just blow right by the atom and not interact with it. So there is an edge step, even in the isolated atom. So the difference between the background and the oscillatory part is the difference between the signal due to the promotion of the deep... And okay, this is a little bit hand-wavy, and some of the people in the back of the room would find fault with what I'm about to say, but it's mostly right. That the background has to do with the part of the absorption that just has to do with the central atom. And the wiggly part is the part that has to do with the presence of all of the other atoms. If you don't have other atoms around, you do not, with an asterisk, do not have any fine structure. And the asterisk is that there are some physical phenomena that do lead to some structure beyond an edge step with an exponential decay. But at the level that we're talking about right now, the background is the part that has just to do with the absorber, and the wiggles are the part that have to do with the interaction between the photoelectron and the rest of the world, if there is a rest of the world. Okay. Sir?
Generally, is the Kweight for the background removal the same as the Kweight for processing of the data?
Doesn't have to be. If you want it to be, it can. But as you're going to find out tomorrow, so that's the only Kweight in the processing. When we do Fourier transforms here in Athena, all we're doing is visualizing the data, right? These two sections of the screen and this just say how it's going to be displayed on this, in the plot window. They're not really processing parameters per se. You will see tomorrow when I start talking about Artemis that the Kweight that we use when fitting the data, you make that decision on the basis of a completely different set of criteria. And that, for me, is independent of that Kweight and independent of how you display the data. So Kweight is situational in the different parts of the workflow through your data. Yes?
The spline clamps.
Spline clamps, right. So the question then is about this part of the screen. So you will find sometimes that you will have data that do this. And you'll find that the background function will do a good job for most of the way, and then sometimes will show a tendency to wing up or wing down, something like that. And the reason is that a spline, by its nature, is well determined in the middle. That is, in the middle, where there's more spline on either side, the value of the spline is very well determined by the data, by having to go through the data. But at the very end, the spline is a bit ill-constrained. In the last few data points, the spline is a bit ill-constrained because there's not more spline on the other side. And you will find in certain situations that without this thing called a spline clamp, that this effect will happen in real data. And it's just kind of annoying because you end up losing the last few points of data because the background is done so wrongly. So spline clamps are a way to try and address that problem. The way it is implemented in IFEFIT, and therefore the way that it's implemented in Athena, is that the last 5 physical points of data in the data file have a clamp applied to them. That is, when the process is done to determine the background function by Fourier transforming and looking at the low-frequency components, the choice of spline will get a penalty if that happens. That is, it's a way, the spline clamp is a way of encouraging the spline to follow the data in the last few data points, even if there isn't more spline on the other side. So that if it wings away, the fit that determines the shape of that function incurs a penalty, and that encourages it not to do that. It encourages the spline to be clamped to the data at the end. It turns out that having a strong spline clamp, that is a big penalty for that happening, is generally a good thing at the end of the data, and generally a bad thing at the beginning of the data, although there are counterexamples for both. The result is that by default, we put a strong penalty on that happening, and that has the effect of, for most data, doing a good job of keeping the spline from deviating from the last few data points of the data. So by default, the high spline clamp is strong, and the choices in there are just 6 rather descriptive words. There is a quantification associated with each of those words, but it's not very interesting what those numbers actually are. The words are quite good enough. Strong turns out to be the good choice for the high-end clamp, and usually you want no clamp at all at the beginning of the data, where nominally you have the same problem, but it's less of a concern for a number of reasons. So, was that an adequate explanation? So, it turns out you will sometimes find some kind of correlation between Kweight and the high spline clamp. You will find sometimes that if you make Kweight of 3 with a strong spline clamp, you get a really bad result. And sometimes if you make this 3, you have to turn off the high spline clamp. Or exactly the opposite. You need to make this small and turn up the spline clamp. In noisy data, there's often a correlation between these two parameters. And if you try clicking Kweight up, you might need to click the spline clamp down. Again, those are the difficult situations where you have to actually think about background removal rather than trust the defaults. All right. Okie dokie. So now, I'm going to get rid of this copy because we don't need it anymore. So that's group menu and remove current group, and it just throws that away. And now I'm going to go and import the other 2 scans that I have of this. And somebody during the coffee break suggested that fun problem that I had right at the beginning might have been due to... Oh, wait, who suggested that? That was... Yeah, it wasn't... I know what it was. It wasn't the space. I think it was the... I think this is going to work. I think it's that I shouldn't have put that apostrophe in. I think I hurt myself by putting the apostrophe in. So that's a bug I need to fix in the software. But I think this is going to work now. So I'm going to import the next 2. And you can import more than one thing at a time. If you have a whole bunch of data, you can use what, in the manuals for Windows, I think they call extended selection. So I'm going to hold down the Control key and click the second one. And now there are 2 things that I'm going to import. I say open, and it does the first one. So it's doing number 100. And it remembers that last time I selected I0 over IT in natural log. And because it noticed that the labels on the columns are the same for this file as for the last file, it assumes that I'm going to want to import the data the same way again. But it stops and makes me click the OK button just in case I don't actually want to import it the same way again. For example, I might also have fluorescence data in the same file, in which case you want to be able to stop and pick a different selection up here. But this is the same, and I want to import it the same, so I'm going to click OK. And now the really nice thing that happens, or the almost always nice thing, is that it notices that the next file the 200, has the same structure in the file, the same number of columns and the same column labels, and it assumes that I want to import that one the same way. So if I had 20 scans that all look the same in terms of the structure of the file, I would only have to interact with the column selection dialog once, and then it will import a whole bunch of data and put them all into this list. And you can see now that we have now 3 items in the list, right? The list is growing. This is probably a good moment to save my work, because it's always good to save your work, particularly when you're using software that the person explaining how to use it started off with by saying it's brand new software and you're going to find problems. It's a really good idea to save your work. So let's save our work. In fact, it's such a good idea to save your work that you may have noticed that as I've been going along, this button up here has been growing increasingly red. And that is me reminding you to click that button before too long. It gets really quite bright red when it's really panic-stricken that you haven't saved recently. So, okay, I'm going to say save, and I'm just going to call it lepidocrosite, spelled correctly. Save. Okay. So the file that I just saved is one of the neater things about Athena, or one of the more useful things about Athena. So the file has all the data and all of the parameters for every data group saved into a single file. That means that I can close Athena, go for lunch, come back from lunch, fire up Athena, read in the project file, and be back in the exact same state I was in when I left. It also means that you can process some data, email the project file to your collaborator who is, someplace else on Earth, but also has a copy of Athena. And then when you're talking on the phone, you can both be looking at the data in the exact same state. So the project file preserves the state of your work. And that's really valuable. It's also, I should say, really valuable for asking questions on the IFEFIT mailing list when all of you join the IFEFIT mailing list, which of course you're going to do at the end of this course because it's the right thing to do. When you ask a question on the IFEFIT mailing list, you can post a hopefully small project file that contains the example of the data that you're asking a question about, and that will make it much easier for one of the experts on the list to actually understand and answer your questions. So these project files are very valuable. Okay, now I've saved, and the program is less stressed, and so now the save button is not only not red, it's actually turned off. But as soon as we start doing things, the stress counter will start counting up again, and it'll start turning red again. So now we have a whole bunch of data, and as you can see, when it imported the first of that sequence of data, the sequence of 2 data, in this 2 in this case, but the sequence of data that you import, it made this nifty 4-part plot again, so that you see that it's used its default values to, process the data to some level. And of course, we can plot in energy, plot in K, so on and so forth. And if we have a bunch of scans on the same thing, and that's what these are. These are just sequential scans that I took at the beamline on the same thing, at room temperature, on the exact same sample. It's nice to plot them together to make sure that they actually plot on top of each other. So the thing to do, as I suggested earlier, is to tick the little box there for each of them. That would be a little annoying if there was a big long list and you had to tick a whole bunch of things. These buttons up here are shortcuts. The A button ticks them all. The U button unselects all of them. And the I button inverts the selections. See how that works? So there are a few other options for marking things which can be found in the Mark menu. for now, I want to click the A button and have them all marked. And click the purple E button. And that shows me my normalized data, all three of them plotted right on top of each other. That's swell. We might want to focus in a little bit closer on the data here, and that can be done in two ways. This is a fairly capable plotting program that I use. So I can, with the right mouse button, just select a region to zoom in on. I can also change the plotting range down here. Each of the tabs for in this drop-down menu are a bunch of different groupings of plotting tools, and there's one for each space, energy, K, R, and Q, and each of them has a box at the bottom for minimum and maximum, which is the range over which you plot the data. So you can also do something like this. Just change the range over which the plot will happen, and now if I hit the purple E button, this plot happens. And looking nice and close in at the normalized Zanes data, we see that on that day at least, my beamline was doing a pretty good job of measuring the same thing from scan to scan. So that's pretty good. And similarly, we can do that. And do that. So at this point, it's finally time to address your question of how is E naught chosen and why does it matter? I'm going to answer why does it matter first. E naught serves at least two purposes in the software, possibly more, but two that I can think of right off the top of my head. One is it's the reference for all these other numbers. So these four numbers right here, as well as things like the plotting range and energy and such, are all evaluated relative to the current value of E0. So where exactly in the pre-edge the ranges for the pre-edge line are depends not only on these values, but also on what that value is. If you make that 10 volts less, then these 2 points will be 10 volts further down in energy because those two numbers are relative to the edge. But E naught also is the zero... Excuse me. E naught is also the zero of k, the point of the zero of k for when you transform to chi of k. Right? When we go from energy to chi of k, we're not only doing the background subtraction, but we're changing the x-axis from energy to photoelectron wave number, which are related. Energy above the edge is proportional to the square of the photoelectron wave number, so we do that conversion of the x-axis. But we have to have a zero of energy, a zero of k. So to demonstrate what I mean by this, I want to remake this picture, but with one of the E0 values chosen to be very different from the others. So we see, if we look at them all, that they're all 7128 point something. So they're all chosen to be pretty close right now. But they're not exactly the same. So we need to get back to the question of how is E0 chosen and what should you do with it as the user of Athena. But let me show you why E0 needs to be thought about. So I'm gonna make a quite substantial change to E0 for just the middle group. I'm going to change it from 7128 to, say, 7124. And that's just an arbitrary change. If we plot the data in energy, we find that there's a very small effect right here near the edge, and that has to do with the fact that the normalization is now done slightly differently because these numbers are all referenced to a slightly different energy. But what's really quite different is when we plot in K, and we see that the second one has a number of things that are quite different about it relative to the other two, one of which is that the details of how it goes up and down, especially right near, out here, the red one is about the same height as the blue and green, but here there are some differences. And also because the 0 of k is now chosen 5 volts differently, you see that there's this shift that goes away as you go to higher energy, which is what you'd expect for given the relationship that energy above the edge goes as the square of the wave number. You would expect that energy shift or that shift of the 0 of k to behave like this. The point being that if you don't think very hard about how you choose E0 for all of your data, things like this happen. So the key then, if you want to visualize your data the way I am here, that is 3 scans on the same thing, and I want to look at them in energy in K and R, well, you have to have the same E0 value. That's half of the story. You have to make sure that they're actually all aligned also. Now, those of you who are lucky enough to do your experiments at beamlines that are some decades more modern than my beamline, you have much better functioning monochrometers than I have. And one of the nifty advancements in the last 20 or 25 years is that these things come with encoders. So when you tell the monochrometer to move some distance through the scan, and then you tell it to go back and start the scan over again, you have some external way other than simply counting step pulses, which can be lost, or you can have mechanical slippage, or something can go wrong. You have an independent way of verifying that when you say go back to the beginning of the scan, that you end up in the same place, and so then sequential scans of data are nicely aligned one on top of another. At my beamline, I have this 25-year-old monochrometer that is sort of a tired old man, and when we move to NSLS2, I think my old monochrometer will be happy to go into retirement, but for the moment we're still using it hard, and we have the problem that when we go to the end of the scan and come back to the beginning of the scan, that we might not be in quite the same place, and there can be probably not a 4-volt shift like I just introduced artificially, but there might be a half a volt or a third of a volt or something like that. So you have to do 2 things to get your data, to get an ensemble of data like this ready for displaying the ways that we want to display it here. We have to align, and we have to make sure that the E0s all make sense. Now, the alignment is not, this is the one shortcoming of these data, is that the alignment is just not very hard because, as I said, my beamline was working quite well the day that, well, we had just serviced the monochrometer, and so all of our mechanical problems were as small that day as they're ever going to be because we had just serviced the monochrometer. And so I picked out of this menu at the top, I changed the view. So this menu at the top changes the view in this part of the screen to let you do all of the other things that the program lets you do. And there's a whole bunch of them. One of them is data alignment. And the way that works, if you happen to go to a beamline where this is really necessary, the way it works is that it chooses one data group as the standard. By default, it'll pick the one at the top of the list. And that'll be plotted in, that will have its derivative spectrum plotted in blue. And then you're going to move around the one that's chosen. So the one that's chosen is the one that it says that it's aligning. And as you can see, the data are in pretty good alignment because the derivative spectra fall right on top of each other. But the way it works is you can align things by hand. So there I just clicked the +5 button, and that moved the red data 5 volts upstream. And that's obviously out of alignment now. You might, at a beamline like mine, 3, 2, 1, you might find yourself in a situation like this. You might have data, and this happens regularly at my beamline. For better or for worse, this is what my data look like often. And they're just not quite in alignment because of instabilities in the monochrometer. So there is an automated alignment feature. Well, you can do it by hand, but there's also an automated alignment feature that will usually do a pretty good job of lining the data up. And even in these data that came out basically lined up correctly, it still decided that in the whole ensemble of data points that shifting by a small amount made a difference. I can do the same thing for the last data group. And now even if I were having this problem of energy shifts from scan to scan, I can correct for that problem by using the alignment algorithm. So now I'm almost, if I return to the main menu, I'm almost ready to plot things on the same energy scale because I've now taken care to align my data. But I don't have the E0s all set sensibly, and we're still seeing this problem here. And when I click on the K button, it will display like it displayed before with that horrible shift to it, right? It still looks icky. So the thing we have to do now is decide what value of E naught we actually want to choose as the value of E naught. And I still haven't answered the question of how is it chosen by the program, but I'll get there in just a sec. What we want to do is use the same value for all the data. Now that our data are nicely lined up, we want to use the same value for all of our data. Well, the tedious, boring way of doing that would be to note that it's 7128.74769. That's a lot of numbers to remember. And click on each one and say, okay, now I need to type that number. I need to do this and type that number in there and then go to the next one. And, if you had a list of 20 scans, you'd be pretty unhappy by the end of doing that. So one thing that we get to do is right-click. If you put the mouse over any of the written labels there and click the right mouse button, a menu that looks something like this will show up. And the first choice pushes that number onto the E0 value for all of the other, all of the other groups, or all of the groups that are marked, that is, that have this tick box checked. And so now I can click there. And if I go and look at the other ones, they have the same number. You can also right-click on that label or the forward Fourier transform label on any of these labels and get a similar menu that instead of pushing a single value on, a single parameter value onto other groups, it will push that group of parameter values. You can also click up on the group menu and set all of the parameters, push all of the parameters onto other groups. So the point here is that you can use those menus to constrain the parameters to be the same across many groups, which is way, way more fun than clicking and typing and clicking and typing and clicking and typing, so on and so forth. So that's a good tool in the program that you should sort of, get as close to your muscle memory as possible because it makes using Athena a lot more pleasant. Once I have pushed the correct value of E0 onto everybody, I now plot in K, and they overplot really very, very nicely. So there's all of our lipidocrocyte data all processed. And we've looked at things now. So way back at the top, when I first got up after lunch and started talking at all of you, I talked about the need to evaluate your data. That is, to know when you've measured enough data, how much data you need to measure, when to stop measuring data. And the sense in which I mean that is this, that any real data is going to have some amount of noise in it, right? This fuzzy little bit out here is just, I'm asserting it's just statistical noise. That is, to my eye, it certainly looks like statistical noise, where you're just seeing some variation around some average of the three spectra, and that's what accounts for the differences from scan to scan. In this case, there's two things about these data. One is I probably shouldn't have stopped measuring data at 15 inverse angstroms because there's still very clear oscillations going on. So I made a mistake if this were a real research project, I made a mistake stopping the data collection at 15 inverse angstroms because there's still data, and the general answer to how far out in K or how far out in energy should you measure data, the answer is keep measuring data as long as there's data, right? Don't walk away from data. If there's something to measure, by all means measure it. Most of the time you won't have data out there, so when you run into that situation, you should, luxuriate in it and measure it all. The other thing about these data is that I would say I'm basically done measuring the data because the level of the noise is really quite small. Even amplified by the k-squared weighting, the level of the noise is really quite small compared to the level of the signal in these data. So 3 scans is probably overkill for these data. But if things were still noisy, then you could estimate the amount of noise in the data compared to the size of the signal and do a little bit of math on the back of the envelope and figure out how many scans you would need to reduce the level of noise down below the level of the signal. And in a real research problem, with a real sample that's probably vastly crappier data than what I'm showing you right now, that's an exercise you would have to go through to decide how much you're going to have to measure on a sample to turn it into useful, analyzable data. So in general, on a real research problem, depending upon the kind of beamline you're at a beamline where you only have the option for step scanning, like at my beamline, you might, in a difficult situation, measure 8 or 10 or 12 scans. But on a slew scanning beamline, such as is being implemented at V18, you might, say I'll measure for a half an hour, and if I'm measuring, a minute a scan, that'll give me 30 scans, or a half a minute a scan, that'll be 60 scans, and by looking at the level of noise, you can determine how many scans you would actually need to measure, how long to scan over and over again, and that tells you how long to spend on the sample. Each individual spectrum may not be the thing that you want to go ahead and analyze because each individual spectrum will be noisy. But as I showed you in my talk on those mercury edge data, one scan was awful, but when I added up 42 of them, I had something I could use. So the next step in data processing is to merge the data. So instead of, if this were my research problem, instead of going off and measuring the scan 0, scan 1, and scan 2 individually, I might instead prefer to merge them up into the average and analyze the average. And that is, in fact, a typical workflow that you would measure your sample for a half an hour or an hour or 2 hours or however long you need to measure it, process your data nicely in Athena, merge them up, and then go off to Artemis and analyze the merged spectrum. And that's a sort of typical workflow through the software. And the way that's done is really quite simple. There's this menu that says merge, and you have several options. You can merge the mu of E data, you can merge the normalized mu of E data, or you can merge chi of k. And the truth of the matter is, and I'll leave this as an exercise for the user, in most cases, these 3 things, you end up with almost exactly the same spectrum. That is, if I were to take these data that I have here and merge them each way and then plot all 3 of them in R, all 3 of the merges in R, they would be very hard to tell apart. In practice, I mostly use the merge mu of E option. And what that does is it adds a new item to the list, which is the average of the ones that were included in the merge. The ones that are included in the merge are the ones that have their box ticked. So if you have 20 scans and one of them happened during the beam dump, so it's not a complete scan of data, and then the rest of the data was measured after the beam came back, you could simply untick the one that happened during the beam dump, and it won't be included into the merge. So the ones that are ticked are included into the merge. What got plotted is the blue is the average of the other 3, and the red is their standard deviation as plotted as raw mu of E. So the standard deviation spectrum would look quite a bit smaller, I presume, if I were to do the merge and normalized mu of e. It turns out that the day I was measuring these, the day that I was measuring these, we were actually running an XATS course at NSLS, and these three scans were measured many hours apart. So there are some scan-to-scan differences just because we don't have top-off at NSLS, and the scans just look a little bit different in mu of e, but they normalized up just fine. And you can now just treat this merged spectrum as data, right? You have access to all the parameters and you can plot it. That is data. It is data that contains the merge of the other three. So you can play with all these parameters and plot the merge as you wish. Now, in a real project, it would be nice, so the next time that you do a merge of something, it's going to be labeled merge 2. So merge isn't a very descriptive name. It's, certainly not something you're going to quite remember what's going on when you look at the project file again in a month. So group menu, rename current group, that's the one. And, I'd call this something like lepidocrosite. And now it's labeled more sensibly. When you save the project file and read it back in, it will be labeled more sensibly. So you can change the names of things so that the whole project makes sense to your brain. And that's pretty close to it. Oh, no, it's not. Yes, I'm finally now going to answer your question. Okay, so where did this number come from in the first place? Okay, the answer is that when the data gets imported, we have to come up with something for E0. So the default algorithm is to look at the derivative spectrum, and we aim to pick the first big peak of the first derivative. Now, IFEFIT has a sort of crude peak finding algorithm that is working really hard to find that as the first big peak in the first derivative and not, say, that right there. That is, it's really trying hard to find something that shows up in the edge. That thing that I pointed out a second ago is actually right here, the inflection point of the pre-edge feature. And it tries really hard not to pick the pre-edge inflection point or the pre-edge peak in the first derivative. It tries really hard to find the peak of the biggest peak in the first derivative. But the way the algorithm is implemented, it tends to overshoot by a little bit. So typically, the default in IFEFIT is 1 or 2 points above the first peak in the first derivative. And that's how it works out in practice normally. So why do we choose the first peak in the first derivative? Well, you can probably make some kind of hand-wavy argument for why the first peak in the first derivative is a sensible choice. That is, it probably has something to do with the threshold of the continuum, probably. But that's not the reason why we choose the first peak in the first derivative. The reason is much, much more practical than that. The reason is that it's not far off. The zero of k is certainly somewhere in here. We choose the first peak of the first derivative because it's easy to explain. So if you're talking to somebody on the phone, you can say, okay, now I'm going to choose the first peak of the first derivative, and you'll both come up with the same answer. So we choose the first peak of the first derivative really for a very practical-minded reason. It's easy to explain, and it's easy to get right. And that's why we do that. Now, there are some other algorithms in the software, and if you right-click on E0, you'll see that you can redo that calculation. That's what the first one is. Choosing this, unless you go and change the configuration of the program. For E0, choosing the default value means use IFEFIT's default. But you could also use the tabulated value for iron K, which would not be a good choice for an oxide because 7112 is all the way down here, and that's not 0 of K. You can set it to a fraction of the edge step, and that fraction is by default 0.5. So that would, in the normalized data, it would be the point that is at 0.5 in the edge. That would be somewhere around here. You can also set it to a zero crossing of the first derivative, and that requires a bit of explanation. So, when you select that one, it first does either using the current value, if there is one, or if you're just importing the data for the first time and you wanted to choose this zero crossing of the second derivative as its default value, it needs to come up with a first guess, which will be this value. It will then look at the second derivative spectrum, which is pretty noisy here, and it will look for the nearest zero crossing. So the point it would find would be that point right there, so just a little bit lower in energy, which actually is the peak of the first derivative. So zero crossing of the second derivative is a common criterion that people use, but you have to define it a little bit carefully because there's a lot of zero crossings. The definition is the one that's nearest to its current or its default value. So that's what all the options are. So that's how the value is found for the first one. You are free to change that value. If you don't like the value that IFEFIT found for you, you can change it. Just type in the box. And then you want to do, like I suggested, you want to right-click and push that value as appropriate to other data groups. Of course, if you're doing a time series of a redox reaction, you don't want to push a value of E0 onto other groups because presumably E0 is changing as a function of time in the redox reaction. So in that case, probably just letting IFEFIT choose its default is as good as anything because that will follow the redox reaction. And there was one other thing I wanted to say about E0. Oh, right. So none of this says what the right value is. All I've really said is how to choose a value consistently over an ensemble of data. And right value is, well, it's a little confusing because, again, because E0 serves two purposes. It's used in normalization. So if you have an ensemble of data and you want to normalize everything so that you can do some Zane's analysis, then you need to choose E0 in a way that the ensemble is processed consistently. And depending upon data quality and how the data is measured, that could be sort of a squishy definition. What I mean by consistently could be a little hard to put my finger on. So you might need to think about what E0 should be for every item in an ensemble of data. The other thing is that E0 is the zero of K, and as we'll talk about tomorrow, and as you may have already seen in your wanderings through XAF so far, that when you do the data analysis in Artemis or a similar program, there's a parameter for shifting E0. And as we'll talk about tomorrow, that is just a parameter that's used to line up the zero of K that you choose at this point with whatever the zero of K is in the theory. So there will be an opportunity to correct that number in the future part of the workflow when you go off and analyze the data in Artemis. So at this level, choose a sensible value that is something in here, not down here, and not over here. Here is not a sensible value, and there is probably not a sensible value, but there or a little bit above or below is probably sensible. Choose a sensible value and do something consistent. Do something similarly sensible for the whole ensemble of data is really the answer there. There's not a right answer. There's just a good answer. And that's the answer to that. All right. There's more stuff that one could, in principle, talk about. There are tools in the software for data calibration, which basically, if you have some reason to believe that the absolute energy scale of your ensemble of data is off, there's a tool for helping you correct that. If you're using a slew scanning monochromator, like they now have at B18, you might need to rebin your data, which is to take this very large array of data because, you know, a typical slew scan, I don't know how you have it implemented. At my old beamline at the APS, we would typically measure about 4,000 points for a slew scan. And that turns out to be much more finely sampled data, particularly in the extended x-axis, than you actually need. And so you do this rebinning step to move the data off of this uniform slew scan grid onto a grid that is uniform in wave number, and that's called rebinning, and you can do that in the program. There are also tools for fixing data if you want to drop a number of points at the beginning or the end of the data, or take glitches out of the data. There will someday be a data smoothing algorithm. It's not currently in the software, even though there's a page for it, that will use a Savitsky-Golay filter to smooth data. That's the plan. And a few other things that you can do. And then a bunch of data analysis, mostly Zane's analysis tools, or data analysis tools, some of which we're going to talk about tomorrow. So there's a whole bunch more things that Athena does. But what we've talked about so far, oh, and I want to actually talk about one of them. What we've talked about so far, though, is the fundamentals, the stuff that you absolutely have to know how to do, and the stuff that you'll do all day long during a measurement at the beamline, which is get the data imported, set the parameters sensibly, and process your data so that you can visualize it in all the spaces. The stuff we've talked about so far is the stuff you absolutely have to know how to do. So this is just about the end of this presentation, and it is, as I said, the things you just know how to do. What I would suggest for those of you who are coming to Athena for the first time is take either some of your own data or some of the example data that I provide and just play around with the software. See how it goes. So we have this practice session coming up for the rest of the day. Just play around with the software, poke at the buttons. And the thing I always tell people at this point, is be childlike. So here's something I've noticed about, a funny thing about adults and children, is children will sit down at a computer and just poke at everything to see what happens. And by and large, adults are afraid to poke at things because they don't want things to go wrong and break things. That is, children have no sense of the consequence of things, and so they poke at things and poke at things until they break. This is what I encourage you to do at this point: is poke at things until things start to go awry. Because the only way you're going to learn how to use the program is to poke at things and see how they work and see, if you change such and such a number, how does the data change? Go ahead and be a kid and play with the program like a kid. The last thing I want to say is there's one other interesting feature in the software, and that is this big blank page that I call the journal. The contents of the journal get written to the project file, so you can write notes to yourself about what you're doing and why you do it. You can put those in the journal, and they will reappear in the future when you read the project file in again. So some of you may find the journal useful to help gather your thoughts as you go through the chore of processing your data. And that's Athena. Any questions? Yes?
I'm afraid it's a fundamental question.
Those are good questions.
Could you explain the relationship between E and R and chi of anything?
Yeah.
Please.
Okay, so I'll do something visual first. Oops, zeros. Okay, So I'm going to use a little data visualization tool that I call an indicator. So I'm going to click on this bullseye button, which this is now asking me to go and double click in the plot window. And so I just double click it near the peak right there. And I click OK. And it said 54. And it turns out that was 54 volts above the edge. Now if I plot in energy again, there's a marker right where I told it to put a marker. I'm going to put another one in, just so that everything is, so that this point I'm making is completely clear. So I'm going to click at the top of that wiggle and say OK. And plot in energy again. Now there are two markers. Now I'm going to go plot in K, and you'll start to see how the wiggles here correspond to the wiggles in K. So these marks showed up at the tops of these two oscillations. So the point I'm making is that there is a one-to-one and onto correspondence between the features in energy, in mu of E, and the features in K. Right? So the place that was marked in energy, the first place that was marked in energy is that when plotted in K, and the second one is that when plotted in K. Okay, I know that's not the full answer to your question. I'm getting there. Okay. So, so K squared is proportional to E minus E naught. The proportionality constant is approximately So the proportionality constant is approximately 3.81. So E naught, so here's our data as a function of energy. Energy being these numbers down here. E naught is 7128. Chi of k is not defined below 7128. So 0, when I click the K button, the 0 is going to be the data point at 7128. And the numbers written across the bottom are going to be related to these numbers by that formula. So let's see if I can do some math just right here in my head. Oh, this is going to be, these are tough numbers. I didn't choose very favorable numbers. So the square root of 54 is about, it's a little bit, the square root of 54 is a little bit bigger than 7. Right, 7 squared is 49, so the square root of 54 is a little bit bigger than 7. So 7 divided by a number that's almost 4 is about 2. So when I plot in K, the first one, oh, I'm way off. What am I doing wrong? Well, I got that. What part? Somebody help me out here. What part of the story did I get so
They're
wrong?
about 2 o'clock, aren't they? Is that from your 0
Well,
to 54 and you?
Okay, let me try this a different way. Let me get rid of this one. Let me do it in a way that I know I can do the math in my head. So I'm going to plot only one marker, 381 volts above the edge. And it shows up there at 381 volts above the edge. Now, let's write that down correctly. That will help. Okay. I think that's more right. Now, 381 volts above the edge, it should show up at 10. So 381 volts above the edge, whatever that is, whatever that energy is, minus the chosen edge energy, 7128 point something, divided by 3.81. And I can do 381 divided by 3.81 in my, which is why I chose that one. And in K, it turns out to be 10. Okay, so that's the beginning of the answer to your question. That's how x-axis relates between energy and K. We do this coordinate transform on the x-axis when we go from energy to K. Okay, but that doesn't explain the transform that goes on the y-axis. The transform that goes on the y-axis is the one that I explained before, where we isolate the oscillations by subtracting the red line from the blue line and normalizing by this number. And then we might also use that K-weighting thing that I talked about. And that's the transform that goes onto the y-axis. So now those two things together, that coordinate transform and the subtract the red line and normalize transform of the data, possibly with K-weighting, is what makes the y-axis. So that's from energy to K. Is that sufficiently clear?
So K is wave number.
K is wave number, yes. Yeah, perhaps I should have explained that more clearly. K and wave number in my brain are synonyms, and I use them interchangeably. Okay. And I will continue to do so, so I hope that won't be confusing.
Not from this point onwards.
Great, awesome. Then, to go from K to R, we do this Fourier transform thing, which is a mathematical function that isolates the frequencies out of an oscillatory spectrum. And you see there's sort of there's certainly one big frequency, and then things like this right here indicate that there are some faster frequencies in the data. And we do this Fourier transform, and we see that there is a dominant frequency. This is the dominant frequency, and then the higher frequency was this one, and there are indeed some other frequencies in that data. And the thing we're going to learn about tomorrow is that this data can be interpreted in structural terms. That is, the location of this peak tells us something about how far, well, this is iron surrounded by oxygen. So the location of this peak tells us something about how far the oxygen atoms are away from the iron atom. But that's sort of a big conceptual leap that I haven't gotten to yet. But that's what's going to happen. That's the big payoff. And that's how you go, that's K to R. So a thing to remember, and hopefully this will be helpful to you. I don't know if this kind of language will be helpful to you. But a Fourier transform is a linear transform. And the salient thing about that is that you don't change the information content of the data by going from chi of K to chi of R. You just change the representation of the data. That and that are the same thing. Just there's a mathematical function that has been applied to present the information in a different way. But they're the same thing. And that's what I mean by a linear transform. And how that all works out will, I hope, make more sense tomorrow when we get to start looking at some theory also. The tools that we use to explain the wiggles. Right now, all I've done is show you the wiggles. I haven't really explained where they come from. Yeah, that's some good television when I drop the laser pointer and pick it up. Any other questions? Like beaten all into submission? One of you coming up for air.
Energy graph. The scale in energy graph. The scale goes from 0 to 1 point. So if you normalize that, they go from 0 to... What's the meaning of those numbers? Or it's just the...
So
the y scale.
the meaning of this number 1 is that we divided through by the edge step, so that the step goes from 0 to 1. getting rid of the effect of thickness, or, you know, when I talked about measuring the sample on this many layers of tape versus this many layers of tape, those would end up with mu plots like this that would look different. They would be different places up and down in a different edge step, because one of them is like this and one of them is like this. But when you normalize, you make all of your data go from 0 to 1. That is what we do when we normalize, is we make the data go from 0 to 1 so that all of our data are then plotted on the same scale. 1 is an almost arbitrary choice, except it's a nice number. I mean, 1 is a good number to normalize to. And it's also the number the theory expects us to normalize to. So that's why it goes from 0 to 1 and not from 0 to something else. And the 0, the meaning of the 0 is it's below the edge. So there's 0 probability of exciting the deep core electron. It's not to say that there's unit probability here, but we normalize these spectrums, so whatever this probability is, it goes from 0 to 1. And then in these data, there's a white line, so, I mean, things work out such that the normalized data has this going up to some value. And that, I mean, what that value is depends upon the material. You'll find if you go measure a rare earth oxide at the L edge, that this thing could go up to 3 or 4 or 5 or something really big. The white lines in those situations can be really quite large. It's just whatever the data does. Uh-oh.
Is there any way you suggest to approach consistently the removal of very high one lines?
The removal of?
Not removal, do approach the graphs of time.
Oh.
When you have high one lines, using the output field.
So the best advice I can give there, and I mean, as you know, because you wouldn't be asking me this question if it weren't the case, that's a subtle question and a difficult thing to do, a difficult thing to say what is absolutely correct. So here's one thing we know. The one thing we know is that, whoops, that's not what I wanted to plot. I wanted to plot this. The one thing we know is that when we get far enough away from the edge, the wiggles go away. So choosing this line consistently, you could almost define that well, because it should certainly follow the data nicely out here, regardless of whether this is a metal or an oxide or a sulfide or anything. The purple line should sort of just follow the data out here. The problem is, and this I suppose is really what you're driving at, the problem is that this is a long enough data range that we're seeing the exponential decay of the step background. So to account for that, we put a quadratic term on the purple line, which means that we've made it a little bit ambiguous where exactly it's going to cross here. And if it crosses a little bit higher or a little bit lower, when we normalize the data, this white line, and indeed everything in the data, is going to be a little bit smaller or a little bit bigger. So the point Gian Antonio is making is that there's an ambiguity in the processing of the data, because our criterion for choosing the purple line, which is our criterion, part of our criterion for choosing this number, is defined way out here, not right up here. But this number is determined right up here. So you have an inherently difficult chore of making the choice of these purple lines consistent across an ensemble of data that might have a varying white line height. Okay, so there I've just stalled by explaining the problem to everybody else more thoroughly. And, you know, I suppose now would be a good time to call for a coffee break so I don't have to actually have to answer the question. So do I have any advice for making it consistent? think I do. So here's an experiment you can do. If you expect that you're going to go to the synchrotron and measure an ensemble of data for which you have this problem, what you want to do is convince yourself in a controlled scenario that you can do the normalization consistently. That is, in a situation for which you know what the answer is, you want to prove to yourself that you can get the answer. If you can do that, then you'll have more confidence that you actually do know how to do the normalization in a way that counts as sufficiently consistent. So what I would recommend in this case is you could get yourself a jar of, so iron isn't the best choice for this, but I'm gonna say it anyway. So you can get yourself a jar of metallic iron powder, and the problem there is that it won't stay metallic, but details. Get yourself, you can do this with platinum, right? You could make something that doesn't oxidize. What I'm suggesting works exactly. Something that does oxidize, you have to think a little bit better about it. Get a jar of the metal, and get a jar of a simple oxide, and measure the two end members, measure, say, 3 combinations. Make a 50-50 combination, a 25-75, and a 75-25, and then do the linear combination thing that we're going to talk about tomorrow, a quantitative Zane's analysis approach. And if you can normalize the data, then do the data analysis and get the answers back that you put into your 3 samples, then you're probably doing the data processing in a consistent manner. So that's another one of these not very satisfying answers, because the truth of the matter is, I don't know where the purple line should cross the blue line. I not only don't know, I don't know how I'm supposed to know that a priori. But you can figure it out a posteriori doing the experiment I described. So when you're a novice, when you're coming to this for the first time, you might need to spend some time not measuring your research project, but you might need to spend some time measuring a sample system, a toy system, for which you can back out the answer to convince yourself that you know how to do the data analysis well. If you do that, that doesn't prove that you will do the data processing consistently for the real data. What it will do is give you some confidence that you can do the data processing in a defensible manner. And that actually, for better or for worse, is sort of the best answer I can give you. And you seem to be nodding, so it seems like you and I are probably in agreement that that's the best sort of thing you can do. But it's a really great question, and I always tell graduate students to do things like that, and almost without fail they say, oh wow, my thesis advisor isn't going to want to waste beam time on that. And really spend the time at the next group meeting to convince them to spend beam time on that. It's an exercise well worth doing and well worth the cost of going to the synchrotron. Because if you don't know how to analyze your real data, then there wasn't a lot of point in measuring it. But if you can prove to yourself that you can defend your work, that's a good thing.